So today we're going to be talking about quadratic forms. Quadratic forms is just another way of saying polynomials with terms of degree 2. In today's section we'll be covering identifying non-degenerate conic sections given their general form equations and writing equations of rotated conics in standard form. So before we get started, let's define what a conic section is. A conic section is the curve obtained by the cross-section of a cone with a plane. And there are two types of conics. There's non-degenerate and degenerate. In this section we'll be just primarily focusing on non-degenerate conic sections, and there are four types. There's ellipses, circles, hyperbolas, and parabolas. So the general form of a conic section is given right here. The general form can also be rewritten in matrix form provided right here. The quadratic equation is equivalent to this right here, x transpose times a times x plus b transpose x plus f equals 0. And the quadratic form can be rewritten as x transpose a times x. And just to keep a note, the matrix A for any quadratic equation in two variables is symmetric. This means that A transpose equals A. If A is symmetric, then any two eigenvectors from different eigenspaces are orthogonal. And this fact allows us to develop a transformation that can be used to develop a map we desire, which will rotate the coordinate axes by the precise angle needed to situate the conic section in standard positions with respect to a new coordinate system. So to pick up where we left off, another definition that we should be aware of is the principal axis theorem. And this supposes that if A is an n by n symmetric matrix, then there exists an orthogonal P matrix and a diagonal matrix D, such that P transpose A times P equals D. And that is, every symmetric is orthogonally diagonalizable. So now let's examine orthogonal 2 by 2 matrices that are rotations. The rotation matrix in two dimensions has the form B and B prime, or B prime. Now, B is the matrix representation relative to the standard basis for R2. The matrix B prime, however, is not relative to any basis and is not a rotation. So to see this, let's Q equal V1, V2 be a basis for R2, and theta equals 0. Then we obtain B prime equals 1, 0, 0, negative 1, and clearly you can see the determinant is negative 1. However, let's analyze a quadratic equation in two variables. First, we start with a conic section with the equation x transpose times ax plus b transpose x plus f equals 0. So let P be an orthogonal matrix that a diagonal is A. So A equals P times B transpose, which tells us D is the eigenvalues of A. So since the eigenvalues of eigenvalue 1 and 2 are the eigenvalues of A, P is orthogonal and its determinant is either negative 1 or 1. And in this case, as we saw, since it was negative 1, we interchange the column vectors of P along with the diagonal entries of D. And this rearrangement of column vectors of P is a rotation. And to obtain the equation for C in the x prime, y prime coordinate system, we are allowed to substitute x equals px prime. So once we substitute it back into the quadratic equation, or what is equivalent to the quadratic equation, we get P of x prime transpose A P of x prime plus B of t P of x prime plus f equals 0. And we can reduce this even further to get x prime transpose times d x prime plus b transpose, so it's x prime and we let b equal, or b transpose p equal d of the quadratic equation. So now we can rewrite everything in the x and y coordinate system as lambda 1 prime squared plus lambda 2 y prime squared plus dx prime plus ex or ey and this equation gives us the conic section in standard position in the x prime y prime coordinate system. And this type of conic section depends on the eigenvalues. So C is an ellipse if eigenvalue 1 and eigenvalue 2 have the same sign, a hyperbola if eigenvalue 1 and 2 have opposite signs, and a parabola if either eigenvalue 1 or 2 is 0. So now let's take a look at an example and see what we can do with it. So in example 1, we have the quadratic x squared minus xy plus y squared minus 8 equals 0. And for this problem, we're going to transform the equation to x prime y prime coordinates so that C is in the standard position with no x prime y prime terms. So first, we obtain the matrix form of this equation, which is given by x transpose ax minus 8 equals 0. And we then calculate the eigenvalues, and so if you use a calculator or an online system, you'll get lambda 1 equals 1/2 and lambda 2 equals 3/2. And then we obtain the corresponding unit eigenvectors, which is v1 equals 1 over root 2, and v2 equals 1 over root 2, negative 1, 1. So this means the orthogonal matrix P equals 1 over root 2, negative 1 over root 2, 1 over root 2, and 1 over root 2, which is just also equal to saying okay. So since, as you can see here, since determinant P is equal to 1, by the previous theorem that we talked about, the coordinate transformation is a rotation. We can then substitute x equals p x prime in the matrix above, which gives us the following equation. X prime and we can rewrite this in matrix form as x prime y prime 1/2. Sorry. If you remember from earlier, this is just another way of saying x prime and then we can simplify this into matrix form given x prime y prime, and D is just the diagonal matrix of the eigenvalues, which is just, as we said before, 1/2 and 3/2. And then we can multiply everything through and obtain the new equation. So once you multiply everything through, you're going to get the standard form, which is equal to So now that we have all this information under our belt, given the equation of a conic, we can find a new representation through an angle. But before that happens, there are a couple of formulas that we need to be aware of. So for this problem, we're told to find a representation of the equation 2x squared minus xy plus 2y squared minus 30 equals 0 after rotating through an angle of 45 degrees. The two equations that we need to be aware of are x equals x prime cos theta minus y prime sine theta, and y equals x prime sine theta plus y prime cos theta. And this will allow us to obtain the new equation after rotating through a given angle. And this equation was obtained by this right here. Once you multiply it out throughout, you get x to equal that and y to equal that. Once we plug in 45 for theta into x and y, we get x equals this after rotating through 45 degrees and y equals that. We found what our x and y values are after plugging in 45 degrees into theta. We can plug them back into the original equation. And so here, as you see, I've plugged in back both x and y back into its equation. And so after foiling it and combining like terms, you should end up with 2x prime squared plus 2y prime squared minus x prime squared minus y prime squared all over 2 equals 30. Now to get rid of that 2, we multiply everything by 2. So once we do that, we should end up with 4x prime squared plus 4y prime squared minus x prime squared minus y prime squared equals 60. And now to simplify it even further, we divide everything by 60, as you can see here that I've done. And once you do end up dividing by 60, your standard form after rotating at 45 degrees is x prime squared over 20 plus y prime squared over 12 equals 1.